In this question, we're asked to calculate the area of a region enclosed by a polar curve. The polar curve is not one of the standard ones, and so the graph is given to you. The name of the polar curve is r equals 4 plus twice the cosine of twice theta. You are not given the theta bounds, and so what you should do to make sure that you are able to figure them out, you should find out that the perception is that theta is from 0 to 2 pi, but to be sure of that, we need to go through the progression of theta using the coordinate angles and figuring out what the r is corresponding with those. When theta is equal to 0 and we plug into this formula, we get 4 plus 2 times the cosine of 0, which is 1. So we're out to 6. And so yes, you're at this point when theta equals 0. When theta is pi over 2, then r is 4 plus 2 times the cosine of pi. And the cosine of pi is a -1, and so that means you should be at 4 minus 2, or 2. And that's the case here. Here's pi over 2, and yes, that's where you're at. Theta equals pi over 2. So it's looking like you are performing this in the order that it's done, and perception is that it goes from 0 to 2 pi. And yes, it does. When you have theta equals to pi, r will be 4 plus the cosine of 2 pi, and that's, 4 plus twice the cosine of 2 pi, and the cosine of 2 pi is 1. So yeah, you're at 6 when theta equals pi. And then you'll finish the rest of that as theta grows to 3 pi over 2 next. You can check it, and then to 2 pi, you'll be back here when theta equals 2 pi. So we just figured out then that theta goes from 0 to 2 pi. Since it wasn't one of the ones that are on the sort of cheat sheet of standard polar curves, we have to go through this process. So we know what theta does. Theta goes from 0 to 2 pi, and then to figure out what's going on with r, remember we slice radially outward from the origin, and so the lower bound on r is r equals 0, and then the upper bound on r is r equals 4 plus twice the cosine of 2 theta. Okay, and when you do an area with a double integral, the integrand is a 1, and then generically we have this dA symbol, and there's 3 options. There's dy dx, and then there's dx dy, but then if it's circular or polar in nature, then we want to go with r dr d theta. The extra factor of r comes in from the Jacobian change in variables. And so we integrate and we get 1/2 of r squared. There's still this outside integral of 0 and 2 pi, and we still have to evaluate at these bounds, and ultimately it means we're going to have to take 4 plus twice the cosine of twice theta and square that out. And so upon doing that, we'll end up with, let's pull the half all the way out, and then we're going to have 16. We'll have 8 of those cosine 2 thetas, another 8, so 16 of those cosine 2 thetas, and then 4 of the cosine squares on twice theta. Okay, and to integrate cosine squared, you have to actually use a half angle identity, and for us that's going to be that the cosine of twice theta squared, well in general, the cosine squared on theta is 1/2 of 1 plus the cosine on twice theta. So if you put a 2 in here, then you'll have to put a 4 in there. So we are looking at the integral from 0 to 2 pi of 16 times the cosine of twice theta, and then with this guy bringing in the formula of 1/2 1 plus the cosine on 4 theta, we'll have a 2 from distributing here, and then a 2 cosine 4 theta from distributing the other one. Okay. Now you can just go ahead and integrate it for sure, and you'll end up with these guys going to 0. Okay, I'm going to actually go ahead and integrate, but I want to tell you that when you integrate a full period or multiple periods of a sine or cosine, it ends up as a 0 area. And so let's just go ahead and perform the antiderivative. The 16 and the 2, it's okay if we put that together and call that 18 theta. There still is the half outside. Okay. And then integrating cosine of twice theta, you get half the sine of twice theta. So we're going to get an 8 sine 2 theta. And then we're going to get a half of the sine of 4 theta, because there's this 2 here, and then you integrate cosine of 4 theta, you get a fourth of the sine of 4 theta. So that's how we end up with that. And since we're going from 0 to 2 pi, these guys are going to zero out. It'll be the sine of 4 pi, and then it'll be the sine of 0. It'll be the sine of 8 pi, and then it'll be the sine of 0. So those guys don't matter. And we'll just have the 18 theta, and that's going to be 18 times 2 pi, but then the half is out there, and that is why our answer to the question is 18 pi. Okay. The cosine of 2 theta has a period of pi, and so when you integrate from 0 to 2 pi, what you have is 2 full periods. And when you integrate a full period or multiple full periods of a function, then the area is going to be 0. So the integral on cosine 2 theta from 0 to 2 pi is going to be 0. Same thing for 4 theta. So you can just incorporate that and just zero them out and not have to actually integrate. The integration is innocent. Go ahead and integrate if you want, but same thing for the 4 theta works as well. So we get an answer of 18 pi for this question. Looks like letter E. Okay. Comment below if you have any questions.